Good morning, all. Today we'll start with some of remaining the morphological operations, and then we will go to the next chapter. The next morphological operation or algorithm or application, whatever you call, is to find convex hull of a given shape, or rather to change the given shape of object such that it will become a convex shape. You know that what is convex shape? That if I will draw a line between between any 2 points of my object, it will be part of my object. Here, if you will see, if I draw a line, it is not part of my object here. It is not part of my object here, right? So if I want to make it is a convex shape. What to do for that? I can have this operation of convex hull. Application of this is a lot of application you know already. In machine learning, you know that convex shape has its own importance, but majorly we will use it for the object detection and recognition purpose. At that time, when we apply some algorithms, the algorithms will work well if the shape is convex. So what we will do, we will apply this convex hull to entire image so that all the shapes are mostly in the convex shape, and then we can identify the object. Right. So what is the operation? What it says that here this is a symbol. If you can recall, this is for hit and miss transform. What I have to do, I will apply hit and miss transform with bi. Um, bi is a structuring element b1 to 4. Four elements I have, b1 to b4. I have four structuring elements, right? And what I will apply with those four structuring elements, I am going to apply. First of all, I will take say B1, one structuring element. I will take B1, and then I will apply hit and miss transform with my image X, right? Then hit and miss transform will give me what, where exactly this B1 with its background and foreground can be located. That is what hit and miss is. If you can recall, the D shape we were identifying. What was hit and miss transform? That hit and miss transform, if you can recall, that how we this was our result, this was our final result. What was that? Where exactly this D shape can be identified? That point, that origin is our answer of the, that origin or that pixel where that exact shape is located. So what I want that now I am having this operation. I am having this operation. You know that how to apply that that a erode your image should be eroded with the foreground. Then your complement of image should be eroded with the background of this. In the procedure, you know, I'm not going to go this in this procedure, but how to identify or how to do this operation in our given image directly without applying that erosion and all those step-by-step operations. So what you will do, you will see that where exactly this B1 is located with its foreground and background both. So in this image X, right? So all those points can be identified, all those pixels where exactly B1 can be identified, that you can have them. And then you will have union of them with your original image A. Actually, what we are starting, you are taking X0 is equal to A. What is A is your given image. Now what you are taking, that for x0 you are applying hit and miss transform with the b1. So in this x0, which is actually a initially, you are finding where exactly this b1 is located. So you will identify that exact location of b1 in that, and you suppose you are identifying this 3 or 4 pixels, then this 3 or 4 pixels should be united with your image a, and whatever result is, this should be called x1. Right? Now, is x1 and x0 same? If not, then repeat this operation. What is that operation? Take your x1 now, take your x1, find b1. If you can find out b1 exactly in x1, right? So, if you can identify, you will keep those points. Suppose these 2 points are where you can identify exact b1 in x1. Then you will take those 2 points and united them with a, and you are going to get so x. Then you are going to get your next value x2, up to which you will continue this. You will continue till you will get x1 is equal to x2. I mean the previous iteration result and current iteration result is same. Then you are going to stop. Then this you completed for b1. Then you will go for the b2, then b3, and b4. suppose result of final B1, that means now you cannot find out B1 more in this result. That means your x1 and x2 are same, or xk and xk minus 1 are same for B1. Then that result we are supposed calling as D1. Then same way we will do for the B2. Then that I will call as D2. In that same way, if I will continue with D4, then if I will unite them, or I will take union of this, then my final answer is called my convex result, convex hull, or that is a convex shape. Okay. For better understanding, we can take this example. Okay. So what I know that I have um, four different structuring elements: B1, B2, B3, B4. This is my foreground. That means this should be one in my. So I will start with my B1. Then I will apply B1. I will identify B1 here in this image. I will locate those points. I will union them with A, and I will keep doing that till I will not find any further change. Then I will go for the B2. Then I will go for the B3. And I will repeat those procedure, and I will obtain D1, D2, D3, D4, and I will take union of them. That will be my final result. Right now, here if you will see, this is interesting structuring element. Here, if you will see that this is my structuring element B1, right? In that, for what is foreground here? Can you identify the foreground here? The foreground is this. This is one. This is one, and this is one. So and here is the origin, but origin value is 0. So here my background is this. This is my background, right? So here background is made up of zeros, and foreground is made up of 1. So this is background, this is foreground, right? And this is don't care. They are cross. They are actually cross. It is not visible here, but if you will see your textbook, they are cross, right? They are don't care. That means they can be 1 or 0. We don't mind about it. So what is our foreground? Foreground is this. What is our background? This is 0. So now you know that in written Miss transform we match foreground and background. So what I have to match? I have not only I have to check where I can find 3 consecutive ones in a column, but also I have to check where I can in the center row I should have a 0 here, and this is the origin as well, right? So I have to identify such locations where I can exactly find out this shape. That is written with transform. That is how we deal with it, that foreground and background exactly matches. So now let us see. Do I have 3 consecutive ones here and 0 here? No. The same look, I cannot even take the rotation of it, right? Exactly this match I should have. Here I don't have 3 consecutive ones and 0 here. Here I have 3 consecutive ones, but not 0 here. So this is also not the match. Here 3 consecutive ones, but not 0 here. 3 consecutive ones, but not 0 here. So please identify the location where exactly I can find 3 consecutive ones and 0. Whatever is here, I don't mind about it because they don't care, right? 3 consecutive ones and a 0. Can I say this is that point that I was looking for? Here I can have here I can get the value. See, 3 consecutive ones and center 0. This can be 1 or 0. I don't mind about them because they are don't care conditions. Now 3 consecutive ones and 0. So this is also that point. 3 consecutive ones, 3 consecutive ones and 0. 1, 2, 3 consecutive ones and 0. So this is also that point. Same way, here I know that I want a blank here, so am not going to check anywhere here because I don't have 3 consecutive ones here. And I will not check here because I don't have 0 here. Where I can check, where I can get this type of shape, I should check only those regions. I am not getting 3 consecutive ones here as well, right? So again, I will check here 3 consecutive ones and 0. Yes, I have it. Do I have 3 consecutive ones here? Still, if I will go here, I don't have 3 consecutive ones because in this iteration, right? So again, this 3 consecutive ones and 0 here, right? So any other 3 consecutive ones can you find out? So these are the points that I identified. Any further point if you can locate, right? So now I obtain exact matching with my x. What was x? X initially was a itself. So I identified where exactly my b1 matches with in a, where I can identify exact b1 in a. So these are those points, right? Now what is my next step? So the hit and miss transform is done. Now what I have to do? I have to union it with a. I have to union it with A. So now what is my new point? If I will union, then this is my new point. This is field, These are my points. Should if I will take union, then how it will look like? These points, these points will be united with this A, and now whatever new shape became, including these points and this point, is now my x1. Is my now x1. You can observe. And my new x, this was my x0, so now my x1 will be so x1. And what is my I am working for b1, and hence it is x1 of 1 is equal to, how it will look like? It will be this shape, gray color, and this as well. Now what is my next step? I have to go for x2. That means what is x2? My k value should be 2, right? I am going for the next iteration for first mask and second iteration, because I want to change my k value, not I value. I'm not going to change this b1. I'm not changing my structuring element, right? So now for that, if I'm going for 2, then I have to take exact match of b1, because I'm not changing my structuring element. Exact match of b1 in x1, because I'm taking for x2. I have to take exact match of b1 in x1. So now this is my x1. Now what is the b1? B1 is 3 ones and center element 0. So where I can find out? Definitely I cannot find out here. Here extra points are added. Can I identify any new points? So 3 ones, because now they are part of my x1. That's why I can consider them. Here there are 3 ones and center element 0. So yes, this is my new point identified. 3 ones, center element 0. I don't care about this, right? 3 ones, but center element is not 0, so I should not go for this. 3 ones, center element is 0. No, it's not 0. 3 ones and center element is 0. So yes, I can say I should. This is my in the next iteration. I should take another color. So this is second iteration with b1 itself. This is second iteration, and this is also second iteration. So this will be the point, because now it is. This is also part of my A, and this is my 3 ones and center element 0. So this is a new one, right? Any further? Any further in the second iteration? I cannot find out. But so this is my x2, right? X2 is equal to x1? No, because 2 new points are added, so I have to go for x3. What is x3? X3 is these 2 points should be united with the previous one, right? So it is united. So this is my new shape. Now what should I go for? X3. X3, for that what I have to take? In my x2 I have to identify this shape, right? So where I can identify it here. I can identify it here. You can say 3 ones, 3 ones and center element 0, 3 ones and center element 0, 3 ones and center element 0, right? So this is in the next iteration. Then it is also united with the previous one. So this is my new shape. Then further iteration, of course, in the new iteration, few more points were added. So I should go for the next iteration. What next iteration says? In the next iteration, if you can identify, this 3 ones and this will be my new point. This 3 ones and this will be my new point, right? Okay, so this is these 2 are points added in the next iteration. So further I should go for the next iteration. What should I take? This united should be taken in the as my base image. In the next iteration, again I have to find out the exact matching, but now I cannot find a new match, because now 2 points were added, but now they are not 3 consecutive ones and 0. So I cannot do anything here. So now my this fourth iteration is equal to third iteration, and hence I should stop with b1. Are you following with the concept? What I have to do? I have to take first structuring element. I have to find out exact location that structuring element can be located in my image. Those points should be united with my image, and that union should be considered for the next iteration. In the next iteration, again do for the same structuring element. Keep doing so till you can find you don't find any change. You should complete it. You should continue with that as we did for B1. Okay, so B1 is over. Now for B2, what to do? For now this is my B1. Now what I have to do? And now we can continue with. Now we have to go for B2. But for B2, how to start? If I am going for B2, that means again I have to start with A. Again, if I will start with A, if you can recall, this was my A. So if I'm starting with B2, again I have to start like B X2, I is 2. So X2, 1, and X0 was A. So again I have to restart with A, but structuring element will be now B2. That's it. Otherwise the steps will be same. So this is my A. If you can recall, this dark color was A. Now what I have to match? I have to match three consecutive ones, and below center element should be 0. So three consecutive ones. But here no need to check because I cannot have 0 element in the next row. I cannot have 0 elements here. But yes, it is possible. Three consecutive ones and 0. So yes, this is the point. Then further, if you can find out three consecutives, this cannot be considered because this was for 1. Now whenever I am going for 2, just keep in your mind you have to start with A. You cannot take previous result. This result that we obtain we will call as D1. D1 we are not going to touch. Now we for to find D2 we will start with A, not with previous result D1. Right? And if you can see these three consecutive elements and 0, so yes, this is that point. So these 2 points, if you can see, are included. Right? So how many iterations are needed here? Okay, so here if you can see, uh, okay, in the previous case, if you can recall, in fourth iteration of mask 1 used, when we did fourth iteration was equal to third iteration, and hence it was x4, that is fourth iteration, k value 4 and mask was 1. So this is actually x fourth iteration and mask 1, fourth and third iterations are same. Here what I did, this is actually mask 2, so actually x2, and if I will do first iteration, this will be my result, and if I will do second iteration, there will be not any change. You can identify, there will not be further change. If I'm adding these 2 points even, then I will not be able to find three consecutive ones and 0, three consecutive ones and 0, and hence my second iteration, if I will do, it will be same as my first iteration, and I have to stop. So I hope you can understand that this number, that is the subscript, is actually indicating how many iterations you did, and superscript is indicating here is which mask you are using. Okay, so in that way, if you will go for X3, sorry, B3, so how many iterations you will need here? How many iterations? 8 iterations are needed. 8 iterations, actually this is the result of 8th iteration, that is up to 7 iteration you are going to expand it. So third mask if you are using, then you will go for 8th iteration, 8, then you will get this result. Same way for fourth mask, if you are completing 2 iterations, that means I hope you can understand that is first iteration is only the different one, second iteration and first iteration is same. So this will be your result, and if you will, and this is actually your D1, this is D2. After all the iteration, whatever results are remaining, D2, D3 and D4, and if you will unite them all, if you will take union of them, and whatever shape you will obtain, that will be your convex shape. That is, if I want to find out convex shape of this will be my final result. Right? So this is the result of convex hull. You can see now if I will draw any line between any two pixels, it will be on the shape itself. And you can see that whose contribution is what. If you can recall, these points were contribution of B1. If you can recall, these 2 points were contribution of B2. These 2 points were contribution of B2, and same way if you will check, other points are contribution from B3 and B4. Okay, so I hope you are clear with it. So what to do? Um, um, Okay, so what you have to do, you have to take first x0 is equal to your image, you have to take any structuring element, you have to find out exact match, and you have to take union with the actual image of those points where you can find out exact hits, right? And that union will be considered as your next, for the next iteration, that will be considered as your base image, right? I hope you are clear with this operation. Now, the problem with this, or not problem, but possibly we don't like one characteristic of this operation is what, that it is expanding the shape. If you can see, this is expanded shape, right? Sometimes it is creating problems. Sometimes if I will convert this into convex, possibly it will join, it will mix with the next object in the surrounding. So it will be difficult to identify that object at that time. So what we can do, we can limit this operation till that. Like if I can expand my shape but not beyond this. I can expand my shape but not beyond this. I can have such limitations. That boundary conditions, I can identify what is my boundary of which are my boundary pixels of my shape, and I can stop. I can have condition on this operation that it should not expand beyond the required boundary. Definitely, it is going to increase the complexity of your algorithm to implement, but it will have advantage that it will not go beyond some point. It will not. It will be faster in convergence because few points to add now, and second that the expansion will be limited, and hence the object will not get mixed up with each other. So if you limit the boundary in your expansion, so instead of expanding in all the direction, your shape, if you can identify this was the shape, only these points are added, only these points are added, otherwise your shape is as it is. Okay. So of course that you can have, that you can identify maximum. You can find out the coordinates where my object is located. This coordinate, this, and this maximum limit you can identify, and then you can put the limit that if it is going beyond this range, stop. Kind of condition you can put. Okay. So any doubt so far in convex hull, right? Then we are going for the next thinning operation. What is thinning operation? For as the name suggests, you are going to reduce the dimension, or if it is a thick object, you are going to make it thin. Thinning is applied that boundaries or expansion is reduced here, right? So definitely you are subtracting something from your original. You are subtracting something from the original. What you are subtracting? You are subtracting exact match of B uh, from A, where exactly B matches that you are subtracting. Now, what is B? B is a set of structuring element B1 to Bn. Okay, and so we will say, okay, but B is not one structuring element; it is set of structuring elements, right? So now, how to do that operation? So this is actually equivalent to, or in another way, we can say this is equivalent to, this definition is equivalent to. First, you apply thinning. You first apply thinning with B1. You can apply thinning with B1. That what you will do? You will substitute B1 value here. That means you will identify where exactly all the points where B1 can be located in A. This is hit and miss transform, right? I am talking about B1. I want to find out thinning with B1, right? So what will happen? A minus A hit and miss B1. What is the meaning of that? Wherever B1 is located, that should be all those locations should be subtracted from A. So can I say some pixels are reduced from A? Because what I did, all the pixels where exactly B1 can be found is subtracted from A. So now they are not part of A, right? Or we can say now A intersection, wherever all those points located, complement of that. This is actually A minus B. This is another definition only, that A minus B is equal to is same as A intersection B complement, right? That you know, A intersection B. This is just definition. But logic wise, both are same, of course. Logic wise, if you want to understand what I am going to do, I will take my B1 structuring element. I will identify where exactly it is located in A, that is hit and miss transform with A. And all those points where exactly B is located is subtracted from A for B1. So that is what I applied here. Then I will go for the B2. Same thing I will apply, that wherever B2 is exactly located, that I am going to subtract from A. In that way, I will complete for all N. So definitely I have removed some pixels from A, so now it is thinner. But this is not the end of operation. Once I completed it, once I did it, then I will repeat this operation. Whatever I obtained from this, I will call it as X1, right? And I obtained X1, then I will go for X2. What is X2? X2 is nothing but the same operation on X1. So further, I will take X1. I will remove all those points in X1 where B1 to Bn is located. Then I will obtain X2. Again, I will repeat this operation on X2. What is the operation? When from the X2, further remove all the points where B1 to Bn are located. I will keep doing so far that x1 and x2 or xk minus 1 and xk are equal, right? So until you converge or until no more points to or previous iteration and the current iteration result is same. Of course, we can understand it with the better example. So this is B1 to B8. So totally I have 8 structuring elements. B1 to Bn if you remember. And what is the operation? This is my A. What is the operation? Operation says identify where exactly B1 is located. Identify where exactly B1 is located, right? Now, if you remember that if I want to do this type of operation, when I come to the boundary points, if you remember, I paired it with zeros. So far, it was not needed because it was my object was in the center itself, and we were just working with center. But suppose I want to check for this condition, I have to put origin here. That means I have to put my sub image or my structuring element like this. So definitely padding with zero is needed, right? So just you keep in your mind here padding of zero is there because I want to work with the boundary elements as well. So far we were not discussing about padding. Initially we discussed, but in the last example we didn't discuss because our object was located in the center. Right, but otherwise if any structuring element you are working with where you are moving your structuring element over entire image, padding is needed for the boundary cases. So now what we want, I want to identify exactly where B1 is located, and all those points I'm going to subtract from A. So now let us find out where exactly this B1 is located. So what is my B1? On the bottom row it should be 1, center element should be 1. This is don't care, I don't care about it. Top row should be 0. First of all, identify the location where top row is 0 because it is easier to find. Here it is all are filled, right? So here only this boundary conditions where this filled with 0, this is padded with 0. Can I say top row is 0 in this location only? Otherwise, this is bottom row 0, but I don't want bottom row which should be 0. It should be top row should be 0. Here in the side, here it is in the side, so not required. Here it can be top row can be 0, but bottom row is not having 1. So this points also I am not interested in. So if you can check, only this points where 3 consecutive zeros, 3 consecutives 1 here, and my center element is 1. That will be this point only. Here if I will check that the 3 consecutive ones will not be there. That's why this is also not the point that I am interested in. Okay. Same way if I will check this is 1, I don't care about surrounding. The bottom row is 1, top row is 0. So okay, this is the point where I will find B1 shape exactly. Here also B1 shape I will find. Here also B1 shape I will find. All these locations. Will this be part of my, can I find B1 here? Will I be able to find B1 here? What is the condition of B1? Top row 0, bottom row all should be 1. Should this point be part of my, or can I say, here I will not find the shape here, so it will not be the result of hit and miss transform. So whatever points I have crossed mark, they are the points of hit and miss transform. So they are the points of hit and miss transform, this transform. But what I have to, this is not my final result. Thinning with B1 means this point should be subtracted from A. So now my new A, the new A is like this. These points are subtracted from A. So this is how these points are now not part of what you can say is not part of A. So actually you can understand that we remove the we reduce this boundary. We shrink this boundary from the top. Okay. So now so this is for B1. Now for B2. So B1 is done, right? So whatever result you are having now, you have to apply thinning over that result further. It is not you have to take this image and then you have to thin it further. Okay, so take this image and thin it further. You have to take this image, not you cannot start from beginning. I hope you can understand the case with in the previous case in convexel we were starting with the original image. Here we are not starting with original. Actually what is that, we want to thin the image, so I cannot start from the beginning, right? Whatever I have reduced, wherever I have reduced, From that I will start, so I can further reduce it. Then I will further reduce it. What I want to reduce here, that I want to identify the points where 3 points are 1, center element is 1, and these 3 are zeros. These two are don't cares. Can you identify any such point here where 3 are ones? No, any other, if you can say 3 are 1, center is 1, but zeros. So what I need, first of all, I have to identify where I can have this type of zeros. Here I don't have this. This is that type of zero, but center element is not 1. So I cannot find any further point which will exactly have the shape of B2. So it will be as it is. If I cannot find any shape, I should move further. So now I cannot find B2 exactly. So no point is removed from the previous result. No points are removed. So this is as it is result. Now go for B3. What is B3? B3 is 3 consecutive ones on this on the left hand side and center element 1. 3 consecutive ones, if you can check here, this is my result. 3 consecutive ones, 3 consecutive ones, and center. No, this is not matching because center is 0 here. What I want, 3 consecutive ones, center also is 1, and so, otherwise 0, or on the right hand side 0, and other are don't care. So if you can check, three consecutive ones, this is 1, that is true, and this 3 are zeros, good, and here these 2 are don't cares. So here this is not don't care, and this is don't care. So we don't care about it, whatever 1 or 0, right? So this is that point, so that should be subtracted. You can see that should be subtracted. And same way, if you will check here, 3 consecutive ones, center 1, and surrounding is and right hand side is also 1, and that is also subtracted. So in that way, if you will continue for B4, B5, right, and B6, B7, 8. So this will be your shape after applying all the elements, all the thinning elements. So what you obtain here is your x1, right? Now what you have to do, you have to check this x1 and the previous x0 is same. What was x0? X0 was your A. X0 was your A. Are these two same? Of course not. So what you have to do, you have to repeat this entire procedure on x1. You will take your x1, again you will check where I can find out b1, where I can identify b2. All these elements you are going to check, right? So that you will do further, that you will do further, and then you will do for all the elements. For the whatever answer you will at last you will obtain will be x2, right? And that x2, and you will check x2 and x1 are same. Then if they are same, then you will stop. Otherwise, you will do continue, and finally, whenever you will get two iterations same, and at that time you will stop, and your result will be this. And this is thinning of this. You can see your object is quite thin now. This is thinning of the shape. Okay, don't go with these notations. I have to correct them. This is having some issues here. I will correct them, but otherwise you should be comfortable with the concept, or the method. Any doubt so far in thinning operation? Any doubt? What you have to do? In thinning operation, what you have to do? So B1 to Bn, n elements, n structuring element. You have to identify in A where I can find out B1 and subtract all those points. Then you go for B2, subtract all those points as well. So keep doing that process for all n elements, and you obtain your final result as x1 and x1 and your x0, or this xk if you obtain, and in the previous operation if you obtain xk minus 1, if they are same, stop. Otherwise, repeat it until the convergence occur. Next is thickening. Thickening operation. The definition of it is a union. In short, see, wherever you can identify B points, all those B points, this is a hit and miss. Wherever you identify B points, unite them with A, because you have to thick it. So you are going to add into A. Earlier we were taking intersection, or we were subtracting. Why? Because we want to thin it. Now we are going to add it. So wherever you identify B, add it to A. That is the definition, right? But B is again set of structuring elements 1 to n. So you first apply thickening with B1. Wherever you identify B1, add those points to A. Then identify B2, add those points to A, and keep doing so, right? But generally this method is not used for thickening. Another method is also there. What is that? The procedure is that this is suppose the shape A that I want to have thickening operation over this. Suppose this is the shape A or this is image A I want to thick. What I will do, I will find out its complement first of all, right? So this is my complement of A, and then I will thin this complement. If you will thin this complement, what will happen? This thickness is going to reduce, right? If you will make it thin, then complement is thinner, then definitely your object will be thicker. What I am taking, I apply, I take complement of it and then I thin it. If complement of A is thinner, then if I will take again the complement, I will get A. This is thicker version of this, you can see. Of course, what is this is a foreground, this is a background. What I am doing, I am thinning my background using the same structuring element that we used for thinning. So I am thinning my background. That means my foreground is thick. It is automatically becoming thick, right? So this is A. But sometimes what happens that unconnected. This is not connected point. You observe. This is totally isolated point. So it is possible that this may result into some isolated points. So you can easily remove those isolated points, right? Um, by checking that it is not having any values in surroundings, there is no value, there is no one in the sun, they are not connected, they are disconnected point, and it is easy to identify disconnected points, right? You can check the connectivity of the whole point, and if it is not having any kind of connectivity, then definitely you can go for removing those points. Okay, now what is so that is what the operation is. Instead of thickening your object, thin your background. Now next operation is skeleton. What is skeleton? Suppose this is some shape, right? Skeleton of is given by this. What is this structure? How if I have some that what we can say the iron rods if I use to make this type of structure, and what kind of iron rods I will need, that you can think of like a skeleton, right? Basic structure. So you can see if I will have this type of rods, then this structure can be created easily, or it will be what can basic shape or inner shape of my object. So this is the skeleton of any object. This type of shape, Y shape object is there. Then this will be the dotted line will be its skeleton. How to see a skeleton? That if I want to make this type of shape, which kind of rods, iron rods, suppose I need to make this type of shape, how I should connect them so that this robust structure can be created, right? Now, or then in this on this type of roads, I'm going to have the stuff. I will fill the stuff, and then the filled stuff will look like this object. In that way, you can see the skeleton. Skeleton itself, and that how basic structure is, so that something is filled over it, so that particular shape is created. Stuffing is done, then the original shape is created. That is what the skeleton is, right? Now, how to obtain this type of shape? So, what you can have, how or otherwise, how to visualize this type of shape? So, you can assume that there is a disk, right? You can have one disk D. What is this? That is maximum disk. What is the definition of maximum disk? That no more disk, no larger disk than that can be accommodated in your shape, entirely accommodated in your shape. Here, if I say different size of my disk, I can have in my shape, I can have different kind of disks, right? But this is the maximum disk that I can accommodate. After that, if I will increase the size, it will not be accommodated inside my object, not over there or not over entire region, right? So this is the maximum size of disk. So maximum disk you can keep in your mind. Now, what is skeleton? How to obtain skeleton? Just think that there is a disk, not necessarily of maximum size. That is the disk you have, which you are rolling over, this entire shape, such that disk should be such that it should be entirely contained in your object, right? Suppose I am having that here, right? So what I will do, I am assuming that I have a disk which is touching more than one location of my object, right? So here it is located. So that origin of that will be considered as part of my skeleton. Then I will roll it. I will move my disc in this direction. So definitely you can see that I can have this type of all these origins have uh, all these origins are part of my skeleton. Now here that disk is the same size of disk. If I will use, it will be smaller. Then I am going to increase the disk size, right? I will increase the disk size. There is no limitation, but you just have to keep in your mind that the disk should be such that it should touch one or more boundaries of your more than one boundaries, rather not one boundary, more than one boundaries of your object, and it should be lesser than the d maximum. What is d maximum? That maximum size disk that can be accommodated in your object. Definitely it will be smaller than that, right? If I will take larger than that size, it will go outside my object. So that size I will change, and that location I will choose. So that location will also be part of my skeleton. Same way, here I have to reduce the size of the disk, but I will have one this type of origins. Here also I will have one type of origin, right? But now further what I have to do, I need to cover this region as well. So I further reduce the size of the disk, and if I will go like this, I will obtain this shape, and I will obtain this shape. If I will roll it over this, and I will obtain this shape as well. So in that way you can visualize. This is just a visualization purpose. This is not for calculation purpose, but how you can visualize. You can visualize that one disk is rolling over that, and all the origins of that can be considered part of your skeleton. Or in other words, if you see that it is a structure where if I will stuff something, then it will make my original shape. In both the ways, you are going to visualize the same thing. This is for the visualization purpose. But now, how to calculate? So for calculation, we should call it as we are calling this as SA, which is which SA is the skeleton. Skeleton. This is our SA. How to obtain SA? It is union of SK. What is SK? SK is defined by this. It is defined by this. What is that? I will take my image A. I will take K value. Suppose my K value is right now say 0. I am starting with small k value, which is 0. I am starting with small k value 0. So I will take A, erode 0 times with B, 0 times with B minus A, erode 0 times with B, opening with B. This is what the definition is. Okay, this is opening. So whatever result you will obtain, it will be for S0. What is S0? Again, I am repeating. Take your image A, for which you want to find out skeleton. Erode it with 0 times. This is how many times you are going to erode with the structuring element B, right? So 0 time you will erode, that means you will not erode. If you will erode 0 times, that means you are not eroding, right? So for the first time you are not eroding, 0 times you are eroding, minus 0 times eroded B and opening with B. This is opening with B, right? So actually you are taking A because you are not eroding with B minus A open B. That is what is for X0 or S0, right? So S0 is with me. I will keep that S0 in a side. Then I will go for S1. What is S1? So we need to repeat this. What is S1? So first of all, what I have to take? S1 is A. One time you are going to erode with B, and minus A. One time you will erode with B and opening with B. That means you will take A erosion B, and whatever result that is that you will have opening with B. Okay, fine. Now, fine. Okay, so now you are having S1. Now, what about S2? What about S2? So S2 is again A, 2 times of erosion with B, 2 times erosion with B and opening with B. Okay. So now that S2, S3, S4, up to which you will continue? You will continue till K. What is K? That K is defined as maximum iteration. That if what I am doing actually, I am eroding A with B. Then I am eroding A with 2 times. I am eroding with B. Then I will. What is the meaning of A? erode 2 times B. What is the meaning of this? That A erode B, again erode with B, right? Then A erode 3 times B, K value 3 means what? A is eroded with B, again with B, again with B. So if you will continue eroding, you know that it is going to shrink, shrink, and shrink. Finally, it may have that it will be totally empty set, right? So what is capital K value? Capital K value is that now it is a maximum value of K. After that, if I will erode, na, that it will be empty set. It is maximum value of K till that A erosion B is not empty set, right? After that, if I will increase K, na, that it will give me the empty set. So that is the last iteration, after which I will do the iteration, then it will make it empty set, right? So it is the maximum value of K till erosion is not empty set. So I will suppose I am having K value 5. So what I will do, I will have as I will find S0, S1, S2, S3, S4 and S5. Then I will have union of all of them, that will be my skeleton. Okay, one more point is there. What is that? If I'm taking my skeleton, right? Suppose I have S0, S1, S2, all points I have, and then if I'm having dilation with K, KB, if I'm having dilation with B, K times. If K is 0, then 0 time dilation. Then so S0 is 0 time dilated with B, S1 is 1 time dilated with B, S2 is 2 time dilated with B, so on. If you are doing so, and whatever result you are obtaining, and if you will take its union for all those dilation results, then you will get your A back. That it is possible to go back from the skeleton as well. Okay, let's see with that example. It is so many operations together, so we can have we can go step by step, so it will be even more clear to understand. This is the image A. This is A, and this is B. Okay. Now, what is my first step? I want to identify first S0. Right? What is S0? S0 is obtained as A 0 time eroded with B, A 0 time eroded with B, that is A itself opened with B. So now first of all, let us go with A 0 time eroded with B. So if I am not eroding with B, I am keeping it as it is. So for K is equal to 0, this is A is same as A is 0 time eroded with B. So that is A itself. K value is 0. So it is same as A. So this is obtained. So this result is obtained, which is same as A because K is 0. Right? Now what I have to do? I have to do opening operation. With whatever result you obtained in the past, you have opening operation with that result. Okay, so whatever result I obtained in the past, I will have opening with that result. What is the opening procedure? What was the opening, if you can recall? That first erosion, then dilation, or what you can see. If you can, if you can accommodate entire structuring element in that, all those points were part of your opening. If you can recall, structuring element, all the points of the structuring element, not only the origin. If you can recall, that was our opening. Right? So you can see that here you can entirely accommodate your B, here you can entirely accommodate your B, here you can entirely accommodate your B. So all these points are definitely part, because my B is same as this shape, it is expanded shape. So definitely these are going to be part of my opening result. This will not be, because here I cannot completely accommodate my B, so they will not be part of it. Here my complete B can be accommodated, and hence all the elements of B, not only the origin, all the elements of B are part of my opening, that we have seen last time in the last lecture itself, right? So this is the result of opening, and if you're not comfortable with it, you can go for first erosion and then dilation with this result, and you will get the same result. This is opening result, right? Okay, so now what is skeleton? So I obtained this, now what is skeleton? S0 is A minus I mean previous result minus current result. So if I will subtract these two results, I am going to obtain S0. So S0 is obtained. Okay. Now So we will go for the reconstruction later. That is a different story. Right now I obtained S0. So I have S0 with me. Now I want to go for S1. K value is changed to S1. What is S1? A minus, sorry, A erode with B. So here this is my A, and same, it was same as my previous result. So A is eroded with B. So if you will erode this, if you will erode A with B, you are going to obtain this point. You know that it will be shrink version. So this is the erosion result, right? Because here you can entirely keep your structuring element, and hence it is part of your erosion. This is also part of your erosion. The origins only. That was the difference between opening and erosion, right? Right. So this is my A erode B. How many times I have to erode? Just once. I have to erode this one. So this is A erode B for K value 1. So this is A erode B. What is my next step? Whatever result you obtain in the previous, perform opening operation here. So you can see here only this is the location where I can put my entire B, and all those pixels of B are part of my opening result. Right? So this is my opening result. I hope you can understand that as well. And what is my next step? S1 is whatever previous result and current step result should be subtracted. So this is my final answer. So this is S1. Okay, so I continue with the K value 1. Now I will go for K value 2. What is K value 2? K value 2, that means A should be eroded 2 times with B. A should be eroded 2 times with B, and the same result should have, whatever result we obtain should be have opening with B. Now, so I have to take A, I have to erode it with B. I know if I will erode it, so 2 times I have to erode. So first time if I will erode, I know I am going to have this result. I am going to have this result. This is first time erosion, and the second time erosion will look like after this I am going to further erode it with B. So what will be my result? You know that here this is the only point where entire B can be accommodated, and hence that origin is the part of my um, my result. So this is actually A erosion 2 times B. Why I use previous result? Because it was one time B already. I know if I will do erosion, I am going to get this result. Further erosion of that will look like this. So this is A erosion 2 times B. So this is that point. What is that opening with B? So now suppose I take this pixel, and where I can accommodate entire B here, I cannot accommodate there. That means that is my empty set. I cannot accommodate entire B here. Actually, what is the definition of opening? Where you can accommodate your entire structuring element. Values of all your coordinates of a structuring element are part of your opening result. But here you cannot accommodate at all, and hence the result is empty set. Now, what is the next step? Subtraction of this two. That means this is your final S2. Fine. Now, further erode this. Now, further erode this. What will be the result? You cannot erode. If you will erode it, it will be 5 set, because you can. What is erosion? All those origins where entire structuring element can be included, but here you cannot include your B at all, and hence it is an empty set. So what is my small capital K value? Capital K value is that erosion, this erosion results into empty set. Before that erosion results into empty set, whatever your value of K or maximum value of K, where after that if you will do erosion, it will be empty set. That's why my K value is 2 here. Capital K value is 2 here. Maximum K, after that, if erosion takes place, it will be empty set. I hope you can understand that point now. Okay, so what we obtained here, so K value is 2, so now I have S0, S1, S2, and K value is 2, so 0, S0, S1, S2 I have, and K value is 2. Okay, so now what I have to do? I have to perform the union. So how my skeleton will look like? Skeleton will look like union of this, this, and this. That means this. Or you can say union. Already we had this S0, then S1. It is united with it, and S2 is united with the previous result. So this is my final skeleton. Okay. What is the next step after this? So this is skeleton. So this is completion of this operation of finding skeleton. But now next is reconstruction is also possible. How to do this reconstruction? For that you have to do dilation. Dilation with what? Your skeleton that you obtain with 0, 0 value of k, 1 value of k, 2 value of k, so on. So I will take my S0, I will take my S0, and I will take the S0, I will take this S0 and perform dilation with B. How many times? K times. Right? Here my K value is 0. So perform dilation with S0, perform dilation of S0 and B should be dilated 0 times. Right? So that means it should not be dilated at all. So S0 as it is. So here my if my K value is 0, dilation with 0 into B or at the 0 B, it is S0 itself. So you can see it as S0 itself. Okay, now what we are going for the next? Then I will go for next value of K, that means S1 should be dilated 1 times with B. So this is my S1, this S1 this is my S1, not this or not this or not this, this is S1. This should be dilated 1 time with B, right? And you know that how the dilation is going to expand the shape. So if you will do the dilation here, you know that here there will be, if my origin is kept here, if my origin of B kept here there is a hit. That means this is part of my dilation. Now if my origin is kept here, if my origin is kept here, it will find the hit, and hence this is part of my dilation. In that way, if you will continue with the dilation operation, you are going to get this structure. So what we did, we took S1 and we dilated it once because my K value is 1. We dilated it once with B 1 time, and we obtained this result as our uh, as our this expression, right? Now we are going for the next value of K, that is K2, that is S2 I have to take this S2. S2 I have to take, then I have to perform dilation with B 2 times, right? I cannot take this result. Why? Previously we took the same result. Here actually this is dilation of S1, not S2. So what if I want to do dilation of S2? I have to perform this dilation operation twice. If I will perform dilation operation once, what will be the result? You know that result will be like this. And if I will perform dilation operation with B, over this dilated result, I am going to obtain this result. Right? And so this is actually S2 dilated with B 2 times. I cannot use previous result because keep in your mind here we were having dilation of S1, not S2. Okay, here why we use, because here this was the result of A and B erosion only, and I wanted A's erosion 2 times, and this was already result of A's erosion 1 time. That's why I used the previous result. Here I cannot use because here base entity is different. Okay, so so now I obtained S2, this is S1 and S0, and what you have to do, if I obtain this expressions, then I have to take union of them, and if you take union of them, and this is union of this and this, and you are going to get this shape, which was our original shape A. So if you have S0 to S2, and if you know the structuring element, it is possible to reconstruct your original shape. Okay, so this is the end of our morphology chapter. Any doubt so far in the skeleton or in thickening operations? Okay, so any doubt in case you have, definitely you can ask me anytime. In the next lecture, we'll start with the image segmentation, a new chapter, image segmentation. Okay, so we'll meet in the next lecture.
A very good morning to all. Today we'll start the next direction of this machine learning, that is ensemble learning. So far, if you just recall the concept that we have covered, we have started with the supervised learning, where we have discussed different versions or different varieties of algorithm which are categorized into either regression or the classification. Next, we have discussed the second direction, where we have analyzed the unsupervised version, specifically clustering, and we have seen many variants of the clustering algorithm, right? And specifically, we have explored three direction: density-based clustering algorithm, distance-based clustering, and the grid-based clustering algorithm, right? And in each category, we have at least seen one algorithm, and in the first category, we have actually seen five algorithms, right? And with this, we'll start the next direction, that is ensemble learning. So let me just present the screen now. So this actually very interesting direction with the machine learning, and maybe you might, if you have referred some research paper, or let's say if you have even referred some material on the internet, you may came across the name like AdaBoost or Forest, the random forest, and so on. Right, so that all are the ensemble learning. The technique is simple. There are no new algorithms, but over here we are ensembling, or you can say we are combining multiple algorithms, right? And instead of taking the output from single, let's say if you think about the classification, so instead of considering the output from single classifier, we will have multiple classifier, and will consider output produced by all that classifier, and based on some criteria, maybe let's say the simplest okay, what could you think about the simplest criteria? So the aim is, let's say we have five classifier, will give same input to five classifier, right? And all will produce something. So let's say we are dealing with image classification, and we want to identify whether the image is of human face or it's not the human face, right? So we'll just have a binary classification where we have 1 and 0, where 1 means the image contains human face, may be one or more, and 0 means there are no human faces in image. Fine. So let's assume that we are training, we have some n number of examples. So we are training, let's say, two classifier. One is a decision tree classifier. Another one is, let's say, logistic regression, and let's say the third one is a SVM. We are also using that SVM, right? So we'll have the three classifier, and all will produce the binary result, that is 1 or 0, right? So we have three output, and we know that the final output should be always single, whether the particular face is human face or not. So what do you think, what should be your strategy to decide what will be the final output? And to be more specific, let's say decision tree produces 1, logistic regression also produce 1, while let's say the third algorithm SVM produces 0. Fine, so what would be your final answer? Right. One, why the simplest phenomena or the simplest algorithm that we can apply is, let's say, the majority vote, or we can find the maximum. So out of three algorithms that we have chosen, two are saying that the output is one. That means the human face is there in the given image. And the third one is saying that the output is zero. That is human face is not there. Right? So the simplest approach that we can choose is the maximum or the majority vote. Right? And we'll finalize that output based on the majority vote. So this is the one technique of ensemble learning. Right? There are many other techniques. So in today's session, we'll see different techniques and we'll try to cover that random forest also. ADA boost we may discuss in the next session, but at least today we'll try to see different approaches of this ensemble learning, as well as we'll try to cover to another important aspect, that is bagging and boosting. Right. So let's begin. So as we have discussed, we have a data set and we'll give that particular data set to some n different algorithm, right? Let's say if it is a classification problem, we have chosen, let's say, four classifier over here. One is the k nearest neighbor, another one is, let's say, naive bayes, another one is SVM, another one is, let's say, decision tree, right? So that will refer as a based learner. Right? There is also one concept referred as a weak learner. Right. So once we discuss that ADA boost, at that time we will introduce that what exactly the weak learner and the fast and so on. And so these are the base learner. That means we'll follow the normal process. We'll give data to that particular algorithm, individual algorithm M1 to M4. The algorithm will train the model. It tune its parameter based on the input and based on the training set. Right. Now during the test time, we will check the performance, or we can say we'll combine the performance result from all four classifier, right? And based on some strategy over here at the next level, we'll have some final prediction result, or you can say final answer. Right, so this ensemble learning we can apply to classification as well as to the regression, ultimately to any of the supervised model. Fine. And one technique that Muktan has already mentioned, that what we can do, we can simplify the majority vote. Right. Another technique that you can use is weighted vote. Means instead of just considering vote of individual classifier, just give some weight to all classifier. So that is also another technique. So we'll see the techniques in a bit more detail. And at that time, we can also think about the probable weighting scenario. How can we weight a particular classifier? How should I decide that this particular classifier should have higher weight compared to the other, and so on. Fine. So this is the basic concept of ensemble learning. So as I mentioned, there are no new algorithm or there is no new technique. What simply you are supposed to do, whichever classifiers that you can combine more than one classifier, and to have a better result, you can combine the result of that classifier, and out of that all result, you can try to predict the final answer. Right, and many research papers show that this ensemble learning, whenever for a particular data set, this ensemble learning is used, it produces the good result compared to individual classifier. Let's say if I just use the SVM, compared to that, if I use the ensemble learning, then the performance is bit increased. Right. So let's formalize the definition. So assume that we have some L number of classifier, and let's say the name of that whole classifier is H1, H2 up to the HL, where let's say the H1 is SVM, H2 is the decision tree, and so on. Right. And the basic idea is to construct a particular classifier, let's say H of X, which combines the result, or you can say which combines the decision of all previously selected classifier, or you can say all base classifier, that is H1 up to the HL. So there are many ways to combine this result. One simplest way is we can consider the vote, right? The majority vote. Another way is for a different member, we will provide a different region. Let's say specifically if we talk about the image. So rather than giving full image to all L classifiers, what we can do, will give part of that image to individual classifier. Let's say we have four classifiers. We'll divide that image into four parts. First part will always give to the H1, the second will always give to the H2, and so on. And based on that part processing, the classifier's result that we obtain, that we will use for further processing, right? So in that case, rather than considering the majority, what we are supposed to do, we are supposed to combine all four answers, right? Or another scenario can be there could be a hierarchy of these classifiers. So let's say we have four part, we'll give all four part to four different classifier. Then at the next level, we'll have one more classifier which actually have this four output as an input. Right? Output produced by the first classifier layer will be given as an input to the second classifier. Right? And the second classifier will produce a final result. So that is also an ensemble learning. Right? So there are many variants of this ensemble learning, how you are actually designing, how you are going to design your final model. Based on that, there are many variants, right? But these are some alternatives, some alternatives to handle this problem, right? And generally it's observed that whenever members have lower error rate, then the performance of ensemble learning is very high. Or let's say if you are using weighted ensemble learning, then whichever member have the higher error rate, higher success rate, that we should choose with higher weight, right? And the requirement, the base requirement of this ensemble is it should contain the diversity. Or main key idea of the success of this ensemble learning is whenever you train different classifier, what happen, a particular classifier may make mistake for a particular input, right? So if I choose multiple classifier, it might possible that the one classifier make mistake with, let's say, human eye. It cannot able to predict the human eye perfectly. Another, let's say, making a mistake with human, other part of our face, maybe let's say lips or something else, right? So the point is, whenever you combine all that classifier, we can expect that together, whenever we join the result, we may have good accuracy, or you can say error produced by individual classifier is negligible whenever you combine the overall result. Right? And generally, we can have a different base learner. Right? That means, let's say, if you recall the previous image, let me go back to the previous slide. So if you see these base learners, we are using four different base learners over here. KNN, another one is Naive Bayes, another one is SVM, another one is decision tree. And it is also possible that you can have one single base learner, but you are using that single base learner multiple times. So that means, let's say we have four decision tree over here. Then we are going to combine the result produced by four decision tree. Question: what will be the advantage? For this given slide, I guess everybody can identify what should be the advantages. We have different learners, so they may make different errors, and whenever you combine the final result, it is very probable that the error produced by a single learner is masked by the correct answer produced by the other multiple learners, right? So that advantage we can easily identify from the given image. But the next ensemble learning approach that we are discussing right now is all the learners are same. Means at all four layer, I am considering, let's say, decision tree, right? We are right now assuming that there are only four learners. But remember that it might possible that there might be more than four learners or less than four learners. It's depend on your need. So let's say we have four learners and all four are the decision tree. So what should be the advantage of this approach? All are the decision tree and all are going to produce the same output. So why unnecessary we should waste our computing power? Any guess? What should be the change in that scenario, or what should be the expected behavior of that particular ensemble learning model? Okay, so keep this question in your mind. Once we see this random forest, I guess at that time the answer to the particular question will be clear, because in the case of random forest, we have the same learners. Right? It's ensemble learning, but over there we have the same learners. Fine. So we'll discuss that. So let's move on. So one practical application that is observed around 2007 to 2009, that is Netflix price, where the goal is we will we are supposed to predict the rating which is given by the user, right? So let's say we know that you can give a rating to a particular movie, right? Let's consider this Netflix scenario. So you can give a rating, but what they have tried in this duration, that is 2009 7 to 9, they tried to predict the rating of particular movie for a particular user. That means, let's say, uh, if I consider my account at the Netflix, right? So whenever one new movie is launched, so for that new movie, that they Netflix team try to predict what would be my rating after maybe watching the movie, or what should be the scenario, right? So what should be my rating for the particular new movie, right? Obviously later whenever I am going to vote, they can verify the rating, but for that prediction they have chosen different criteria. One can be users rating for the other movies. So can anyone identify what would be the benefit of the first criteria, or what would be the goal to select this first criteria, users rating for the other movies? Right. So the aim to including this particular feature is, so see, whenever we consider this machine learning or data science field, so sometime in the past also I have mentioned, might be during the previous lab itself, that whenever you are in the learning phase, you always have the Excel, right, where you are supposed to have the classification and so on. But actually in a real world scenario you just have the data, so you have to filter out the data, you have to find the features, you have to find the examples, and then later you need to find some techniques of pre-processing, and then you can use some model, right? So consider this Netflix scenario, so they have the data, right? So for whenever you consider the data per user rating so far, right, whichever movie that he or she has rated, that information that they have, right? But from that information they are supposed to identify some features. So here we have a list of some features, right? There might be many features, right? Only these three features are not necessary, but how can you select the feature? So this, the way to select the feature must be clear, and that way always varies from application to application or definition to definition, right? So as you guys are saying, the Jainik as well as Daria, the role of the first feature is to identify users test, right? We are supposed to find which kind of movie he or she likes, right? So once you identify that, let's say for a particular person, once you know that this person always like the comedy movies, so he always rate the comedy movies to, let's say, 5 or the maximum what. But whenever it comes to some other category or other genre, he is always going to give, let's say, lesser number of votes. So you can predict for a new movie what should be the vote based on this feature. So this is one of the important feature, right? So let's say the new movie is comedy, you can expect the higher voting from the particular user, oh sorry, higher rating from particular user, right? The second criteria is other people's rating to that particular movie, the new movie that is recently launched. So So what is the role or need of this criteria, or what we can derive from the second criteria? Right. So what other likes? So, but what will be the impact of other people's rating on, let's say, my rating, or let's say my output? So how it relates to a particular user? Right. So overall, we can say how good the movie is, right? As the area is suggesting. So what we can say how good the movie is based on the general or the overall rating. So let's say I haven't given a particular for a particular movie, I haven't provided the rating, but right now many people are saying that the rating of that particular movie is 5. So it is very high probability that I will also rate it as a 5 after watching a movie. The reason is because generally whenever it's a very good movie, then majority of people will definitely like that, right? Majority of the people. Right. So that is the grouping, right? Or you can say the clustering. So clustering also comes into this picture, Ghata. So as per the Ghata's, so if you refer Ghata's answer, so what's he trying to convey is whenever you consider a group, so to find this group or the cluster, we need to see the past result, right? The rating history of particular user, and you can compare that history with the other users. And wherever the similar choices are found, then you can consider the rating for new movie must be or might be similar to the other users, those who belongs to the same group, right? And this technique is many time used in this recommendation system, right? And in the previous semester many of you have or I guess one or two group have tried that recommended system, and over there they have followed this approach. So based on the past rating or past review, you can compare different user, and you can see you can find the group of the user, those who have the similar liking and disliking. So based on that, you can recommend something to a new user, or let's say you can recommend something to the existing user which other user has already bought, or let's say which other user has already tried. Fine. So that is also one good feature whenever you select whenever you have this kind of application, maybe the recommendation system or let's say this rating system. Now just read this third feature and try to identify what should be the use of this third feature. Actually, rather than feature, we can say this is not included in the system design. Right? No other information related to the movie is provided to the system. Right? So we are providing some information, let's say users rating, then what other people are, what is the scenario of other people's rating, and so on, but we will not provide any other information related to the movie. Another information maybe the abstract summary of the movie, or let's say the actor, who are the actors, who is the director, and so on. So right, we are not providing that information, but just based on the rating we are supposed to predict the other users rating, right? So that was the definition given by the Netflix team. And such application is many time referred as a collaborative filter, also called collaborative filtering. And the price was 1 million to the first team, which do around 10% better than the Netflix system, which was at the time of 2007 to 9, right? And the winner group, if you see the winner group performance, what they have used this ensemble learning, and they have combined the rating of around 800 different system, right? Or you can say they have used 800 different learners, the base learners. Fine. So this is, you can say, one benefit of, or you can say, the practical application of this ensemble learning. Right. Any doubts so far? Okay, so let's move ahead. The one thing you always need to consider is whenever you have this ensemble learning, it occupies more resource compared to more computing resource compared to the other single classifier, right? As you have multiple classifier and you are going to train all them together, or even if you are going to train it one by one, then also you need the larger training time as well as you need such large computing power, right? So that you can say one limitation of this ensemble learning. But right now, if you consider the current scenario where the supercomputer as well as cloud processing is available, then this limitation is negligible, and we can always try for this ensemble learning whenever we have the larger number of data and whenever we want the higher accuracy, and the single model is not able to produce the appropriate result, right? So now let's see different approaches of combining multiple classifier. Right, as we have begin the session with the discussion of the simplest approach, that is, we can just club the result of all the classifier and based on the majority vote, we can decide the final result. Right, so that is referred as the averaging, where the final hypothesis, or you can say the final result, is always a vote of all the members, right? Whoever, whichever class have the higher number of vote is considered as the final classification result. Right, so this, the first approach is this averaging, right? The simplest and the very straightforward approach, where this x is an input, so we'll give that same input to all the learners, all the base learners. And if you can recall, we have L different learners, right? H1, H2 up to the HL. All that will produce some output, the classification result. We are going to average that result out, or you can say from that we'll find the majority vote, and whatever is that average result, that would be the final output of this averaging ensemble learning. Fine. The second approach is weighted average. So now, instead of considering the direct results, if you just see this figure, the initial portion is same to the previous one, right? We have x, that is input. We are going to give that x to all the classifier. All the classifier will train on that, will all will adjust their parameters, and during the test time all will produce some classification result. Now, instead of just combining that result, whatever is the result, will multiply that result with some weight, or you can say with some probability, right? So that weighted result will combine, and once again the result which have the highest weight will be considered as a final output. So it might possible that, let's consider the simplest scenario where we have 5 learners. So it might possible that in this scenario, that is weighted average, the output produced by 2 learners, let's assume that out of 5, 3 learners produce 1 and remaining 2 produce 0 in case of binary classification, right? So in this scenario, it might possible that the output produced by the 2 learners only, that is that 0, will get will be produced as the final output if the 2 learners will have the higher weight, right? And this weighting is generally identified, the weight of all these classifiers are identified using the validation set, right? So try to recall the initial lectures of this machine learning, where we, instead of dividing our data into just two sets, that is training and testing, we should divide, or we can divide it into three category, that is training, validation, and the test set, right? And many times the validation set is, you can say, some isolated set from the training set itself, and sometimes they are dedicated parts too. So from the validation set, we are supposed to identify the weight for all the learners. And so can you think of some strategy to decide this weight? The previous scenario was easy, right? We are supposed to sum up the result, and where whichever whichever have the majority vote, that will be the final answer. But over here, we are supposed to give some weight. Let's say W1 is 0.2, W2 is 0.7, and so on. So can you think of some strategy to decide this weight using the validation set, right? We will not decide this weight value from the training set. And as you all know that we will never touch up the test set during this training phase, that during this training process. Right, and what's the name? We can use the method used in artificial neural network. Okay, anyone else? Are you talking about the backpropagation, Jamin, or anyone else can, if you can recall the name? Okay, backpropagation. So this backpropagation is actually a method to, let's say, if your neural network, or let's say whenever you consider that neurons, and if you want to update the weights of that neuron, then you can apply that gradient descent into the backward direction, and that is actually the backpropagation, where we will start from the last layer and we'll move back towards the first layer, right? And we'll apply that all weight updation till the beginning, or till the first layer. But in this ensemble learning, there is slight modification. Whenever you decide this weights, let's say whenever you decide this W1, W2 up to WL, remember that this H1, let's say this H1 itself is a neural network. Let's assume that H1 is the one of the neural, let's assume that H1 is the CNN, right? Let's say the H2 is the logistic regression. The HL is, let's say, the decision tree. Fine. So whenever we consider the H1, which is the neural network, so during the learners are ready, or you can say that are freezed. So H1, let's say, have 100 parameter and that are freezed, right? All the 100 parameter contain something. H2, let's say 500 parameters, so all are freezed. So they all are already trained, or you can say all are already modified on the training data set. But now we are introducing some new weights, and that new weight is actually deciding the priority, or you can say the importance of a particular base learner. So let's say if I say W1 is equals to, which means let's assume that the final sum of this weight is 1, right? So and let's represent this weight as an probability value. So whenever I say W1 is equals to 1, so I can say in the overall final decision, I will consider 20%, there will be 20% impact of this H1 learner, there will be 20% impact of this H1 learner, right? So whenever you decide this W1, W2 up to WL, And let's say whenever we adjust that weight based on this validation set, we will not throw that weight back to this H1's parameter, H2's parameter, or HL's parameter, right? So we'll not go beyond till this X during the adjustment of this W1 up to the WL, right? Whatever you want to do, you should do it over here only, right? You should not back propagate that values towards this H1, all the parameters of H1, as well as the weight which are associated with the X also, right? So X and some weight multiplied with this H1. Fine. So we'll not back propagate that result back to this learner. So because this is not the part of the training, or you can say this weight W1, W2 up to WL are not relevant to the original data. They just represent the importance, or you can say the performance of the previous learners. So right, so that training should be separate, or you can say that updation should be separated from the weight updation of individual learners. Right. So we can definitely use the back propagation, but remember that whenever you apply the back propagation to update this weight, we must stop at this layer. Right? It's not like the neural network where but actually the back propagation means starting from the last layer and we'll move towards the first layer. Right. So this is not the neural network architecture, but rather than this is just the combination of multiple learners where one single learner can be a neural network. I hope I'm clear. Right. So now you have a validation set. So remember that whichever technique that you apply, maybe let's say if your neural network and if you apply the back propagation to one or more than one of these learners, and you freeze the parameters, right? And you are right now at this layer and you need to decide W1, W2 up to WL. So now to deciding this W1 up to WL, we need to identify 2 points. Just refer this statement. We will decide this parameter using validation set. Why? The second question, the training set, the testing set will never use, right? So no need to discuss about the testing set. But why we are not using training set to decide this weight W1 up to the WL? And the next question is why we are using this validation set for that purpose? So can you think about the answer of this question? So to answer this question, first let's make it simple. Whenever you consider the validation set and think about any one learner, let's say think about this H1 only, right? Forget about the other. Think about the H1. Let's assume that H1 is the neural network. So now, whenever you consider this validation set, what do you think? The samples or the examples which belongs to this validation set are previously seen by this H1 or not? Right, Jainam, Jamin. Not 100% correct, but nearly correct, right? Because it has already seen that examples, right? So the point that Jamin has mentioned, and what Gata is saying, training set is used for individual model. Now, when we want to see how much each model contribute, if we use a training set, all will give the maximum accuracy, right? Correct. So both of you have the same point to mention, and that's actually the reason. Fine. So if we try to see the performance on this training set, that is already known to all, right? So all are already tuned to the training set, right? So all have already adjust their parameter or adjust their weight based on the training set. So it is not useful or beneficial if you apply the training set to adjust this weight W1 to WL, but rather you should give some unseen examples to them, right? So we have two unseen set. One is the final test set, and the one is the validation set, right? So we know that the test set will never use for any kind of training, and any kind of training means training of model or training of this ensemble parameters, right? So what we can do, we can have separate validation set. Now during the adjustment of this ensemble parameter, So these are not the parameter of any model, right? So W1, W2 up to WL are independent to all the models. So now whenever you give some new set to all the models, what we will see, will observe the performance of all H1, or let's say H1 is getting 50% accuracy on validation set. H2 is getting 90% accuracy on validation set, and so on. So let's assume that we just have H1 and H2. So which of them will have the higher weight? Let me repeat the question and let me make it more interesting. Let's say we just have two learners, H1 and H2. H1's accuracy is 150 in training and validation respectively. H2's accuracy is 90 and 80 in training and validation respectively. So which of them will have higher weight, either H1 or H2? Right, correct. Right, Muktan as well as Kata. So we know that in the case of H1, though it gives you 100% accuracy in the training data set, but for new examples, for new data, it cannot able to give you a good accuracy. So it should have the lesser weight compared to the H2, which is almost consistent. Previously with the training set, it gives you the 90%, while with the validation set, it gives you the 80%, right? So it almost consistent with the original training data, which is already seen, as well as the new data set, right? So we should give some higher weight to the H2, right? So this, you can say, a major factor to decide the weight value of all the learners, right? And that's why we are introducing this validation set. So I hope it's clear how can we choose this weight, right? So now you can use this method. Let's say the back propagation, if you want to use, you can use this back propagation and you can adjust the weight. But to adjust the weight, you should focus on the performance of validation set, not the training, not the testing. Fine. So this is the key idea behind this second model, that is weighted average model of this ensemble learning, right? The next and the third model is with the use of gate, the gate mechanism, or you can say the gating feature, right? So now we'll have one more function. We'll refer that function as a gating function. It behaves like a gate. So now this W1, W2, W3 up to WL, the value of that weight depends on this get function. And once again, we'll train this get on the validation set, right? Along with your training input, right? So you can just consider this gate as a kind of barrier for a particular learners, right? So depend on the sample, you may have different weights for different learners, right? Instead of keeping it as a same for all the scenario, or you can say for all the cases, we can identify using this get mechanism or the get function, we can identify some behavior of all this algorithm, and we can detect that in this kind of scenario this algorithm performs best. For example, let's say you want to identify the vehicle, or you want to classify the vehicle, and the classification is, let's say, in terms of bike, car, and let's say the non-vehicle category. Fine. And using this gating mechanism or the gate mechanism, you have identified that H1 is going to produce a very good result whenever the input is bike. Right? It almost with 95% accuracy, it can detect this is a bike, but it cannot detect well whenever the car is there. Right? I'm considering very small example: car, bike, and non-vehicle. But actually, let's say whenever you have 100 or 10 classes, which is you may find it in the ImageNet or some other real world data set. Fine. So I guess ImageNet have the 100 classes, or yes, 100 classes, right? So out of that 100, you may identify using the get mechanism that for this 2 or 5 classes, H1 produces very good result. For the remaining, let's say 7 classes, H2 produces very good result, and so on. So whenever that similar feature is there, whenever similar output is there, what get will do, get will change the weight of particular learner, maybe H1, H2, or the HL. Right? So the coefficient of this individual member depends on the input, right? So based on the input, we will update that value. And so this is a slight difference than the previous version. I hope you can identify what exactly the difference between the weighted average, which was the previous scenario, and this getting mechanism. Where in the previous case, the weights are fixed. But now in the current scenario, the weights are variable. Depend on the data, this getting function will update the weights. So once you have the new input, the W1, W2 up to WL will change. Next, for the other input, once again, it might get different values of weight. Right, and that values will be controlled by this get. Right, so simply you can consider it at this getting function as a real gate, right? So what is the role of gate? To control the input. Let's say if you consider the any gate, so the basically the role is to control the input within the room, right? Or you can say whenever you want to enter the room, it depend on the gate, whether let's say the gate is fully open. Many at time, maybe let's say many people can enter into the room together, but let's say if I open the gate only half at the half layer, then it might possible that at a time only one person can enter into the room, right? So similar mechanism is used over here in this getting, and it always varies based on the input, right? And the another way is this stacking. So we'll create this stack, right? So in few slide back, I've just discussed this version where we have multiple layers. So instead of considering or instead of combining the result of first layer learners, what we'll do now, whatever is the result of first layer learners, we will use that result to have, or you can say to train another learner. Let's say the second layer learner, and once again the second layer you may have multiple learners. It depend on your need, right? And once again this second layer is trained on the validation set only, right? So during the training phase there is no existence of this C, and C can be any of the other classifier. Let's say C can be SVM, C can be DSSP, and so on. And so during the training phase, we do not have such connections, so we do not have the C. We'll just train this H1, H2 up to the HL individually. We'll adjust its weight. But now with the validation set, we'll try to observe what is the output of H1, H2 up to HL, and that output will give without any operation, or you can say without any weight, we can give that output to the second layer, that is C, which might be some other classifier. Right, and this C will adjust its weights based on the validation set input, right? So it consider its weights on the validation input. Fine, and you can also have one more modification or one more change over here. Instead of passing all this input, or sorry, all this output of H1, H2 up to the HL directly to the C, you can once again use weighting mechanism or the get mechanism over here. Right, so you can control what should be passed to this C. Right, so this kind of complexity you can always achieve whenever you are designing this ensemble learning. Is it clear? Next, how can we achieve the diversity? So in an initial slide, we have just said that the ensemble learning are useful whenever you have diversified data, right? So there are many chances of mistake. What the mistake means, whenever you consider particular classifier, it may make mistake in some of these situations. There are many other situations, but let's say these are the three very common situation, right? So one is, let's say the pattern was very difficult. That means whenever you consider some feature, so there are no relationship between the feature as well as the learning algorithm that you are trying to apply, right? So it's just in random. So no matter matter whichever classifier use, whichever classifier you combine, if there is no pattern, then no one, or let's say no classifier, can predict the good performance. Right. So no matter whether you use it individually or if you use it with this ensemble approach, none of them can give you the good accuracy or good performance, right? Because in your data set, or you can say in your input itself, there is no pattern. Another problem with which might reduce the performance of classifier is, let's say the classifier is getting overfitted. So if it is a overfitting, we know that if we change the training set, it is possible that we can avoid this overfitting, right? So instead of having the similar training set, we can apply some modification, right? So there is one technique based on this overfitting avoidance in this ensemble learning. So we'll see the technique in more depth. And the next reason for the mistake, or let's say next reason for misclassification, is this: some features are noisy. Right? So now instead of wearing the training set, what you can do, you can change the input features. So in overfitting, you can say you are changing the rows, and in this third case, you are changing the columns. Right? And in the ensemble learning, it is also possible that instead of giving the same examples to all the learners, we will give different examples during the training. Also, we'll give different examples to different learners. Right? It is also possible to give different features to different learners. Right? And I guess from this statement you can imagine, if you have the same, even if you have the same learners, still you may have different result, right? So my first question in the starting of this lecture, the one version of this ensemble is, we can have same learners everywhere, right? Let's say this is entry, this is entry, this is entry, all are the this is entry. But in that case, what can you vary? The input which you are giving to all that decision tree, as well as the feature that you are giving to that particular decision tree, that you can vary. Fine. So in that scenario, they will produce a different result because they are trained on different feature, or let's say they are trained on different examples. So they will produce different results, right? So that is also a way to train this ensemble model, right? And that way is actually referred, whenever you consider the decision tree, the combination of the decision tree in the ensemble learning is referred as a forest. Fine. So we'll see that forest. But before that, this two technique, the whenever you are having a training data, is I have just mentioned the another point, that you can vary a training set, you can vary a feature set, right? So there are many ways to manipulating this training data. And to be specific, this bagging and the boosting are two approach which are used in this ensemble learning to vary the training data. And why we are varying this training data? To achieve this diversity, right? So approaches that we have seen so far, that approaches are same. Remember that whichever four approaches that we have observed, just the majority vote, then the weighted average, then the next is this gated result, the stack, right? So that all approaches are there. But now next level, what we are doing, we are changing the training, right? So whichever are the base learner, we are changing the training of the base learners, right? So for that we have these two approaches. One is bagging, another one is boosting, right? So let's introduce this terminology, that is bootstrap replication. So we have, let's say, capital N training examples, and from that we'll construct a new training set by sampling, or let's say by considering only small n instances, and that is with replacement. And the replacement means, let's say we are excluding around 30%, or once again, this 30% is just one threshold, right? So you can consider any other threshold. So in this bagging approach, we'll create bootstrap replication of the training set. And we'll train our classifier for each of the replica. And to observe the performance, we'll consider the data which is out of the bootstrap, right? That is that you haven't that classifier haven't sent so far, right? And the average output of all classifier will be the final result. Fine. So that is the concept of this bagging. Right. So boosting we'll see probably in the next lecture, but this bagging let's try to cover, or let's try to see this bagging concept into the more detail. So assume that this is your data set, the full combined data set, and we'll divide the data set into two parts, let's say training and the test data set, right? And the training from the training data set will further divide it into the training and the validation set. Right. So now from this training data set, we'll create different bag. Right. So let's say this is the bag number 1, this is the bag number 2, this is a bag number 3, and let's assume this is a bag number 4. And let's assume for simplicity, we are going to create 4 bags. Right. So this all 4 bags and the size of that bag are less than n, where n is the total training examples. So in this all 4 bags, we will have different number of, or let's say we'll have less than n number of examples, right? It's fine if some repeated examples are there. So let's give some number. Let's say n is equals to 100. Fine. So let's say in a bag 1, we'll have 70 example, randomly selected 70 example. Let's say in bag 2, we'll have randomly selected 55 examples, right? So obviously you can observe that the 55 and the 70, so there might be some repetition in these two bags, right? So there might be some data which is repeated, or you can say which are present in both the bags. Fine. Then this third bag, let's say, contains 60 number of examples, right? And the fourth bag, let's say, that contains 50 examples. Fine. Now we have these 4 bags ready, and let's assume we have 4 different models. So we will train individual model on a particular bag only. That will not give any input from the other bags to the particular model. And so this, let's say, is model 1. So model 1 is trained on all the samples of bag 1. Model 2 is trained on all the samples of bag 2. And so on for the model 3 as well as for the model 4. Right. And then we are combining the result produced by all 4 model, and that is via the voting approach, right, that we have just seen. Right. So this overall concept is referred as the bagging. So if I just quickly summarize this bagging, instead of giving same input to all the base learner, what we are doing, we are dividing that input into different bags, and all bags, there might be some repetition of the data in different bags, but we will train a particular model on a particular bag only. Instead of giving the full training set, I will just train it on a particular bag, right? And whichever after the training, whichever result produced by this model, I am just going to combine, and maybe the combination is via voting approach. Right? So there are many alternations. Instead of having the different size, you can have same size. Let's say all will have 50 50 50 50. Right? But this is widely used approach where different bag have different number of samples. Right? So we'll see this random forest as well as the boosting approach in a next lecture.
Hello everyone. So in the last session, we have gone through operator precedence parser that is one special kind of bottom-up parser. Today we'll start the main topic of bottom-up parsing. We have parsing which is known as LR parsing. So we'll consider today a new topic, that is LR parsing. And this parsing technique will definitely take 4 hours to understand. We have 4 lectures to understand this technique. Let us see what is LR parsing. So the most powerful shift-reduce parsing, and also it is efficient, is known as LR-K parsing, where L stands for left to right scanning of the input, which we want to reduce to the starting symbol of the grammar. R indicates rightmost derivation. We will consider the rightmost derivation. And it is a bottom-up parsing, so it is in a reverse order. And K indicates a look ahead. We will take the K as 0 or 1. LR parsing is attractive because LR parsing is most general non-backtracking shift-reduce parsing. It is a non-backtracking parser. It is based on shift-reduce approach. The class of grammars that can be parsed using LR methods is a proper subset of the class of grammars that can be parsed with predictive parser. So any valid example of LL1 grammar, any valid example of LL1 grammar which we have parsed using a top-down approach can be parsed using LR1 technique. So LL1 grammar is a proper subset of LR1 grammar. So any grammar which we have parsed using LL1 technique, we can parse using LR technique. Also, we can parse much more grammars which we cannot parse in LL1 technique. It is more efficient. So LR parsers covers wide range of grammars. We have 3 main techniques in that: SLR, simple LR, canonical LR, that is known as CLR, and LALR, intermediate LR parser. SLR, LR, and LALR work same, only their parsing tables are different. The parsing table, similar to we have done a parsing table construction in top-down parsing. Here we have to also construct the parsing table. But for all the 3 techniques, the tables will be different. So this is the basic block diagram of LR parsing. We have input A1, AI up to AN. We have N symbols in the input. The string which we want to validate, we want to parse. We have LR parsing algorithm. We have a stack. In stack we have S0. So S0 indicates a current state of the DFA, state 0. S1 is the state 1 of the DFA. SM is the state M of the deterministic finite automata. So basically, through this LR technique, we are constructing a deterministic finite automata. That based on it, will decide that where to move from one state to another state, so that we can get the complete reduction. And X1, X2, Xm minus 1, Xm can be terminal or non-terminal of a grammar. So in the stack, we have state as well as terminal and non-terminal of the grammar symbol. In the LR parsing table, we have 2 parts, action part and the go-to part. In case of rows, we have states. The states indicates rows of the table, and column indicates terminals and $sign in the action table. We have 4 possible actions: accept, reject, shift, reduce. In the go-to table, we have rows indicates states of the finite automata, and the column indicates a known terminal. An element of this go-to table will be a state number. So it will tell that from state 1 we can go to state 1, 2 or 3 or 5. So it will specify the state number. So basically in LR parsing we have the main thing, the construction of action table and the go-to table. Once we know how to construct action table and go-to table, we can easily parse the string. So there is one example grammar. This is one example grammar. We have E gives E plus T. Then we have E gives T. T gives T into F. And T gives F. F gives within parenthesis E. F gives ID. So here you can see this grammar is a left recursive grammar. Still we can use that grammar. This grammar is a left recursive grammar. We have a left recursion in the grammar. E gives E plus T. So such grammars we cannot use with top-down parsing technique. Here we can use this grammar. So you can see we have action table and go-to table here. We have states from 0 to 11. We have a finite automata with 12 states. We have terminal symbols here, ID plus star, opening parenthesis, closing parenthesis, and dollar. In the go-to table, we have 3 known terminals. So we have 3 columns, known terminal E, column for known terminal T, and column for known terminal F. So now we'll see how to construct this table, how to generate the states. Let us first use this. Let us assume that we have this table with us and we want to use this table on the given input so that you can understand the basics of this SLR parsing. So now we'll take one input and we'll see that how we'll use this table. So initially the state will be 0 in the top of the stack. Our input is ID star ID plus ID dollar. Our input is ID star ID plus ID dollar. So now if I consider the table, then from state 0, you can see from state 0, first row, here, state 0, and we'll go to S5. We'll go to S5. It indicates that we have to perform a shift operation and we have to go to state number 5. We have to perform a shift operation and we have to go to state number 5. That's why you can see 0 ID 5. So we are shifting ID from the input and we'll go to state 5. So now you can see on the stack you can see clearly that we have a combination of state and symbols. We have a combination of state and symbols. State is 0, then ID, which is a terminal here, and then state is 5. Now, if you look at this in the table, then you will find that for state number 5, you can input star. So here you can see in state number 5 and input star. This indicates a reduction by rule number 6. This indicates a reduction by rule number 6. So that's why what we have to do is we have to do a reduction by rule number 6. And when we are doing the reduction, we have to eliminate that part. So now what we are doing, we have reduction by rule number 6. So now this ID 5, this ID 5. So this both state as well as this symbol. So whatever is the length of your production, here you can see length of your production. If I consider this as alpha gives beta, then length of beta is 1. Length of beta is 1. Now 2 times the length of beta. 2 times length of beta we have to pop from the stack. So we'll pop ID and 5 from the stack. Here we'll pop ID and 5 from the stack and we'll do a reduction of ID to F. Now as we are doing a reduction from ID to F, we have to consult the table at 0 and F. So you can see from state 0 and F, we are going to 3. From state 0 and F, non-terminal, we are going to 3. That's why here you can see this thing. This is how we'll do a first reduction. Now, our top of the stack is 3. Our input is star. Our top of the stack is 3. Input is star. So again, we will consult the table. Our stack is 3. Input is star. So it indicates reduction by rule number 4. We have to do a reduction by rule number 4. So again, it is P use F. F is a non-terminal. So length of beta is 1. So we have to pop 2 times beta. So we have to pop 2 symbols from the stack. So we'll pop F and 3. We'll pop this F and 3 from the stack. F reduces to T. F reduces to T. And 0 and capital T. So now in this table, 0 and capital T will get. From this table, we'll get 0 and capital T as 2. So we get 0 capital T 2 on the stack. Now for state 2 and input star. For state number 2 and input star, you have to consult the table. State 2, input is star. This indicates S7. This indicates S7. S7 means what? We have to shift symbol on the stack. We have to shift the symbol on the stack and we have to go to stack number 7. That is what we do here. We'll shift the star on the stack and we'll go to state 7. Now we are in state 7, our input is ID. We are in state 7, our input is ID. Again we will go to this table, to the state 7 for input ID. For input ID, it is indicating shift 5. It is indicating shift 5. So we have to shift the input. So you can see we are shifting ID on the input and we are going to state number 5. We are going to state number 5. Now it is state 5 and plus. It is state 5 and plus. So again we consult this table. We have state 5 and input symbol is plus. It is indicating a reduction by rule number 6. Reduction by rule number 6. We have to pop 2 symbols on the stack. So we will pop this 2 symbols from the stack, ID and 5. ID reduces to F as per the rule. Now 7 and F. Our state is 7, top of the stack is F. So 7 and F. 7 and F. We are getting 10. So 10 will be the new state. 10 will be the new state. Now 10 and plus. We have to consider 10 and plus. Now state number 10, when input is plus, it is reduction by rule number 3. It is reduction by rule number 3. Reduction by rule number 3 means what? The length of beta is 3. Length of beta is 3. So we have to pop 6 symbols, 3 into 2. We have to pop 6 symbols from the stack. So as we pop the 6 symbols, this 10, F, 7, star and 2. These are the 6 symbols. Up to T. Up to T. So T, then 2, star, 7, F10. 6 symbols. The 6 symbols we have to pop. We have to pop these 6 symbols. And as we pop this symbols, this reduction by t, because t into f reduces to t. Now it is 0 and t. Is it clear? Because t is also on the left hand side symbol. Because this t is there, we are copying this t into f. We are copying t into f, 6 elements from the step. But here also on the left hand side of the root, we have a non-terminal t. That's why we are pushing t again. Do not confuse that this t is not as it is. First we'll copy this t to multiplication 7, f and 10. All these 6 will be copied. Then because we are doing reduction by root, we'll push non-terminal t, which is on the left hand side. We are pushing a non-terminal t, which is on the left hand side. And then 0 and t, 0 and t. The 0 and t gives us, as per the rule, 2. This 0 and t gives us 2. That's why we have 0 t and 2. That's why we have 0 t and 2 on the step. Okay. Any query up to this step? Any query up to this step? Yes, any query up to this? Yes, is it clear? Yes. Is the last step clear? Okay, so now let us proceed further. Now here it is 2n plus. It is 2n plus. Because 2n plus will go to 2n plus. It is telling it is a reduction by 2. It is indicating a reduction by 2. So further we have to remove this e and 2 symbols from the stack. We do a reduction by this. E reduces to e. So now it is 0 and e. It is 0 and e. As per the table, 0 and e, it gives us 1. So that's why we have 0 e1. Now it is 1 and plus. Now it is 1 and plus. Now if I consider 1 and plus, then this 1 and plus indicates S6. This 1 and plus indicates S6. Because of that, we have to shift plus on the stack and we'll get the stack 6. Now 6 and ID. Now 6 and ID. Again, we'll consult the table. 6 and ID. It is S5. It is S5. So we'll push ID on the stack and we'll go to step number 5. Now 5 and dollar. It is 5 and dollar. We'll consider state 5 and dollar. It is indicating reduction by rule number 6. So ID reduces to F. We'll pop 2 symbols from the stack. We'll pop these 2 symbols from the stack. ID and 5. ID reduces to F. Now 6 and capital F. 6 and non-terminal F will give us 3. This 6 and F gives us a 3. We are getting 3. Now 3 and dollar. Now state 3 and dollar. It is indicating reduction by rule number 4. Reduction by rule number 4 means We have to reduce F to T. We'll pop two symbols from the stack. F and T will be popped. We get 6 and T. Now 6 and T. From state 6 and T, we'll get this 9. We'll go to state 9. So now we'll have 6 T and 9. Now 9 and dollar. 9 and dollar. So if you consider state 9 and dollar, you will find it is reduction by rule number 1. It is reduction by rule number 1. State 9 and dollar. It is reduction by this rule, E plus T. So we'll pop 3 to 6 symbols. So this all 6 will be popped. We'll pop all these 6 elements. E1 plus 6, E and 9. These 6 elements. E1 plus 6, E and 9. We'll pop all these 6 elements. So now 0 and E, because reduction is to symbol non-terminal E. So 0 and E. Now this 0 and E will give us 1. You can see 0 and E. That gives us 1. So now we get 0, E1 and dollar. Now 1 and dollar. Now this 1 and dollar. This 1 and dollar. This gives us XM. This gives us XM. This is how we can accept the thing. That means the string is proper. The string is proper. So also here you can see in this example that what we have done a rightmost derivation. Basically, we have done nothing but rightmost derivation in the reverse order as per the rule. You can see here that first, if I consider the rightmost derivation, it is E gives E plus T. First step. Now rightmost non-terminal is T. Now here rightmost non-terminal is T. We will derive from T F. Derive from T F. So it is like this. From E we are getting E plus T. Now rightmost non-terminal is T. So we will derive F from T. Now F is the rightmost non-terminal. So we write E plus ID. We will replace F with ID. So you can see it is the rightmost derivation. Now for E we will have T. We get T plus ID. Now for T we have T into F. We have T into F plus ID. Now again rightmost non-terminal is this F. So we write T into ID plus ID. Now T is left, so we write F plus ID into ID. Now for this F, we write ID plus ID star ID. Basically what we have done a rightmost derivation in this reverse order. You can see first we are considering this, then we consider the second one, and here third one. The rightmost derivation exactly in the reverse order. We have done rightmost derivation exactly in reverse order using this shift reduce approach. So what we have done so far is we have just used the table. We have just used the table, action and go to part. So the action part having the information of shift, reduce, and accept, and all the empty cells indicates or reject. If you start doing some empty cell, then it is a reject. The string is not valid. Okay, now any query in this technique? Yes, any query in this technique? This comes. example clear? Yes. Is the example clear? How we have done a shift reduce parsing using the table? Yes. Is the example clear? Okay. Where is the query? In which step? Let me rejoin. Yes. Is the last step clear? Yes. We will now. Yes. Yes. Yes, clear? Okay, now let us proceed further. Basically, what we have done is now here what we have done is this is our calculation of LR parser. So in the stack you can see we have S0, X1, S1 up to Sm. We have a combination of state and input. We have a combination of state and input in this stack. Right? In the input part we have only terminal symbols.
Hello. Now, can you hear me? Hello. Can you hear me now? Okay, so that's better now. Let us continue. And can you see the screen? Okay, so basically in this configuration, we can see we have a stack symbols which contains a states of the finite automata, and we have terminal and non-terminal symbols. And on the other part, we have the remaining input and dollar at the end of the input. So it is nothing but a representation of what we have done in the previous slide. So you can see in the state we have a combination of states and terminal and input symbols. We can have terminals, non-terminals, and states in the stack part. And in the rest of the input, we have the input and the dollar. So that is what the configuration of LR parser. So from one configuration, we'll move towards the another configuration. And as we know, initially we have only S0 on the stack. So now the most important thing is we have to understand various actions which we have performed and how to construct this table. So now here you can see shift S. So basically what it tells that we have to shift the next input symbol and the state S onto the stack. So you can see here that our state is SM. Our state is SM and our input is AI. So based on this information, state and input, we'll shift the symbol AI on the stack, and we have a new state. We have a new state S. So this is what we have done also in this example, that you can see in the first step. Our state is 0, our input is ID. So we are getting ID 5. So we are shifting the input and the new state available on the stack. So same thing is here. Reduce also we have seen that what we are doing, we are popping the 2 times beta, where beta is the right hand side of the production. We'll pop 2 times beta symbols from the stack. We'll push A, and according to the previous state S and A will get the new state. According to the S and A will get the new state. So here you can see that we have some symbols here on the stack. So now we are doing a reduction. So some symbols R, you can see here 2 times beta is considered as R. So we are popping that many symbols from the stack. So now as a result we are getting S M minus R on the stack, because once you pop some symbols from the stack, what you will get a state which is just below the some elements from the top of the stack. So we are popping the symbols from X M minus R plus 1 to X M. All that symbols are popped and corresponding states will be popped, and we'll do a reduction by non-terminal A and we'll get the new state. So this is what we have done in the reduce step in this table. So it is nothing but a description of this, that we are popping these symbols. So now 0, and we are doing reduction by T, so 0 and T will give us 2. So this is nothing but this reduce step. It is just a general representation of it. Next we have accept. If the parsing is successful, we'll go to state 1 and dollar. If parsing is successful, we'll go to state 1 and dollar. So that is your accept. And last is error. If there is any empty cell in the table, then it is known as error state. So now let us consider how to construct this table. That is the most important thing, LR0 item set. How to generate these states. So an LR0 item of a grammar G is a production of G, a dot at the some position of the right side. So now when we construct LR0 item for any rule, so here we have one grammar rule, A produces small a, capital B, small b. So and we have 4 possible LR0 items for that. A produces dot small a, capital B, small b. Then A produces A dot capital B, small b. A produces A capital B dot small b. Then A produces small a, capital B, small b and dot. So we are putting dot at some position on the right hand side. So this is known as LR0 item for the given rule. So what is the meaning of this? So this indicates the first one. This first indicates that we are waiting for small a, capital B and small b. We are waiting for small a, capital B and small b. Once we'll get this, we'll reduce to capital A. The second rule indicates that we have already got A. It is small a dot capital B, small b. So we have already got small a. Now we are waiting for capital B and small b. We are waiting for capital B and small b. Third rule indicates that we have already got small a and capital B. That part is already received. So now we are waiting for small b. Once we'll get the small b, we can do the reduction. And this last indicates that we have got small a, capital B and small b already on the stack. So now we can do a reduction to capital A. So this is nothing but your handle. So this is known as LR0 item. So now from this what we will generate? We will generate a collection of sets of LR0 items. From this we will generate a collection of sets of LR0 items to construct the table, which is known as canonical LR0 collection. And we'll add the new production in the grammar, that is S dash gives S, and we'll tell that this grammar is an augmented grammar. we'll add the new production. S dash gives S, and we'll consider this S dash as a new starting symbol. We'll consider this S dash as a new starting symbol, and this is how we'll augment the grammar. So here S is just a representative. You can take the first symbol as a starting symbol. So now to generate this item set, let us see how we can generate this item set. If I is a set of LR0 items, if I is a set of LR0 items,
કનેક્ટેડ છે આ વાઈફાઈ એમાં મારું જ ચાલે છે
ના ચાલતું. Yes, are you able to hear me? Are you able to hear me? Okay, so now if I is a set of LR0 items for a grammar G, then closure of I is the set of LR0 items constructed from I by the two rules. We have to construct a closure of I. So if A gives alpha dot capital B beta is in closure of I, and beta gives gamma is a production rule of G, then beta gives dot gamma will be in the closure of I. We will apply this rule until no more new LR0 items can be added to closure of I. So basically what this tells that A gives alpha dot B beta. So we are waiting for non-terminal B and beta. Once we get, we can do the complete reduction. So now to get a non-terminal B, what we have to do is we have to actually do a reduction for B, because then and then we'll get non-terminal B on the top of the stack. Is it clear? Alpha dot capital B beta. It is alpha dot capital B beta. So now when it is alpha dot capital B beta, so it means that we are waiting for non-terminal B. But non-terminal B we will not get from the input. Yes. Are you getting this? Yes, can you hear me? Yes, can you hear me? Okay, so now let us understand. Hello, can you hear me?
Yes. Now, you can see here added rules for once we are getting the rules. Once we are getting these rules for E, then we have to add the rules for D. We have to add the rules for D. Because here E gives dot P. Because it is E gives dot P. Now because after dot we have a non-terminal T. After dot we have a non-terminal T. We have to add the rules. E gives dot E star F and E gives dot F. Now here you can see after dot we have F. After dot we have capital F. We have to add the rule. F gives dot within parenthesis E and F gives dot I. This is the most important thing. First we have only one rule. E dash gives dot E. We have only one rule. E dash gives dot E. Now because after dot we have a non-terminal E. Because after dot we have a non-terminal E, we'll add two rules. E gives dot E plus T and E gives dot T. Now you can see that dot and T, because after dot we have a two non-terminal capital T. After dot we have a two non-terminal capital T. We add the rules. E gives dot E into F and E gives dot F. Now again you can see that after dot we have a non-terminal capital F. After dot we have a non-terminal capital F. Because of that we have add the rule. F gives dot within parenthesis E and F gives dot I. We have add this rule. We have to add this rule so that this will be the closure of the first one. This is the closure of E dash gives dot. So now another important operation is a go-to operation. So now basically go-to tells how to construct the go-to table. This go-to tells how to construct the go-to table. We already have this first. With this we already constructed. E dash gives dot E. E gives dot E plus E gives dot E. Now E gives dot E into F. E gives dot F. F gives T. Parenthesis E. F gives dot I. Now we will get this go-to. So go to E. That means from this I0, from this I0 or I, go to I comma E. That means if you cross the E, if you go to E, then what you will get? So we have to shift the dot towards right. You have to shift the dot towards alpha dot x beta is there, then we have to find the closure of this alpha x dot beta. We have to find closure of alpha x dot beta. So now first I will consider this. Go to IP. We have two rules with plotting. We have two rules with plotting. So I will write like this. E dash gives E dot. We'll shift the dot. And E gives E dot plus T. Now E dot plus T. This is what we are getting. E dash gives E dot. After dot we don't have any. Similarly, E gives E dot plus T. After dot we have a terminal. This will be also the closure. This will be the closure. We are getting this closure. Go to IP. Now similarly we have another symbol. After dot is T. We have another symbol after dot is T. We'll consider E gives E dot. We'll consider E gives E dot. And from this we get E gives E dot star F. We get E gives E dot star F. The second one. Now again you can see after dot we don't have anything. And here after dot we have E star, which is a terminal. So it is a complete thing. It is a complete thing. Now similarly for go to IF, we have one rule. We have only one rule for F. Is E gives the only one such rule. E gives dot F. So when you consider go to F, when you consider go to F, is E gives F dot. Is E gives F dot. Now the most important, go to I opening parenthesis. This is very important. Go to I and opening parenthesis because in the item set I, we have total 5 symbols. We have total 5 symbols. We will write for all the symbols. Go to E, then go to E, go to F. Now it is go to an opening parenthesis. Now when I consider go to opening parenthesis, we will get this first one. We have this one. F gives opening parenthesis dot E closing parenthesis. We are getting this F gives opening parenthesis dot capital E and closing parenthesis. Now you can see this dot capital E. We are getting dot capital E. After dot we are getting a non-terminal. After dot we are getting a non-terminal E. We have to add the roots for that. We have to add the roots for that. That's why we are adding the root. E gives dot E plus E. Is it clear? Because after dot we have a non-terminal E. In this we don't have a non-terminal. In this second one we don't have a non-terminal after dot. Here we don't have a non-terminal after dot. But here after dot we have a non-terminal E. That means we are waiting for reduction of E. We have to consider roots for E. So we add the root E gives dot E plus T and E gives dot E. We add these two roots. Because after dot we have a non-terminal E. Now as we are adding these two roots, again we are getting this situation. After dot we have a non-terminal E. After dot we have a non-terminal E. So we are getting this dot E star F and dot F. Now this rule, last you can see after dot we have a non-terminal F. We have a non-terminal F. We are adding the roots for F. We are adding the roots for F. F gives dot within parenthesis E and F gives dot I. This is the most important thing. And if you get a non-terminal after a dot, then you add all such roots. That is what the closure of the item set. We have to consider the closure of this report. So now, if I consider the whole thing, I will get things like this. This is what we have done. I0, it is gives dot E. have done the first step. T dash gives dot T. So we are adding the T productions. T gives dot T plus T and T gives dot T. Now we have dot T. So we are adding the T productions. T gives dot T into F and T gives dot F. We are adding the F productions. F gives dot within parentheses T. F gives dot I. Now we calculate O2 from this I0. So I0 and T. This I0 and T. We are getting T dash gives T dot and T gives T dot plus T. If you consider O2 operation. We go to I0T. Now similarly go to I0T. We are getting I2. Similarly from go to I0F. If we go to this, we'll get T gives F dot. Now for this, we'll get go to I0 opening parenthesis. Here we have go to I0 ID. It is I0 and ID. So it is only one. F gives ID dot. F is ID dot. Now from this I1, from I1, what we will go to I1 and plus. Because here dot is at 10. Here dot is at 10. So we have to consider go to I1 plus. We calculate this go to I1 and plus. So what we have to do, we have to shift dot towards right. We get E gives E plus dot T. We get E gives E plus dot T. Now because it is dot T, we have dot terminal after dot. We have to add the T production. We have to add T productions. E gives dot T into F and T gives dot F. Now because it is dot F, after dot we have F. We'll add the F production. F gives dot within parenthesis E and F gives I. Now from this E gives T dot. It is already complete. Dot is at the end. Now from this we can get go to I2 star. Let's go to I2 and star. We write T gives T star dot F. We shift the towards right. Write T gives T star dot F. Now because it is dot F, after dot we have a dot terminal F. We have to add the F production. We have to add the F production. Now this is complete. T gives F dot. It is already complete. Now here, go to I4 and E. We have to calculate go to I4 E. Go to, then we have I4 item set and we have to consider dot use. We have two such rules with dot capital E. We have two such rules dot capital E. So shift the dot towards right. And write F gives opening parenthesis capital E dot closing parenthesis. And E gives capital E dot plus T. This is what we get. Because here after dot we have terminal symbols. Not in that any. Now from here, E gives dot T. So it is go to I4T. This go to I4T. So E gives T dot. And T gives T dot star F. Now you can see when I write this go to I4 and T, I will get the same as I2. Here, when I calculate go to I4T, it is E gives T dot and T gives T dot star F. It is same as I2. It is same as I2. Similarly, now go to I4F F. This key gives F dot. This key gives F dot, which is same as I3. Now go to opening parenthesis, I4 and opening parenthesis. This I4 itself. This go to I4 and opening parenthesis. This I4 itself. Similarly, go to I4 and ID. It is I5. It is I5. Now, if you consider I6, now this is your from I6, go to I6 and E. This go to I6 and E. I6 and E. It is E plus E dot and E gives E dot star F. We get I9. Now similarly go to I6 and F. Go to I6 and F. It is I6 and F. This E gives F dot. E gives F dot is nothing but I3. Now go to I6 and opening parenthesis. It is I4. It is same as I4. Similarly, go to I6 and ID. It is same as I5. Now let us go to I7 and F. I7 and F. So here it is. Go to I7 and F. From I7 item set and F is E star F dot. Because only one root is there, it's not F. There is only one root with dot F. It is E star F dot. We are getting I10. Last, if I consider from directly I8, go to I8 and closing parenthesis. We get I11. From go to I8 and closing parenthesis, we get I11. Now, if I summarize all these things, we get this kind of diagram. From I0 on T will go to I1. From I0 on T will go to I2. From I0 on F will go to I3. From I0 in opening parenthesis I4. I0 and ID will go to I5. Similarly, if I consider I9, from I9 star will go to I7. From I7 on F will go to I10. I7 and opening parenthesis is I4, I7 and ID will go to I5. We'll get this kind of deterministic finite automaton. Why it is a deterministic FA? Because from every symbol we have one outgoing error. From I0 state we have outgoing error for E, F, opening parenthesis and ID. So it is a deterministic thing. We don't have multiple outgoing paths of the same. So, is this item set construction clear? How we have constructed this item set? Because this is the art of LR parsing. In every technique, we have to construct this item set. And to construct this I0, I1, I2 up to I11 is the most important thing. Is the most important thing. Yes, is it clear? Is it clear how we have constructed this item set using go-to operation? Yes? Is it clear? not clear to anyone. Because all are speechless. Nobody is telling yes. How to generate from IP to IP1 from here. That's why you are not giving the answer. Let us stop the session here. Anyway, we are running out of time. We will not get started.